Welcome back. Today we're going to start learning about vectors. And the first thing that I want to do, I want to explain to you the difference between scalars and vectors. So what is the difference between scalars and vectors? Well, look, you have some quantities in the world that you can measure for which you only need one number line. For example, let's take mass, right? So in order to describe mass, you only need one number line. So we measure it in kilograms, for example, and then we have 0 kilograms. We can have 5, 10, and etc. kilograms, right? Or another thing would be, for example, money. We could have dollars or euros or pounds. And then again, we could have minus 200, minus 100, 0, 100, 200. Here you would have something like profit, and here you would have something like loss, or how much money you have and your debt, like whatever your context is. Another scalar quantity would be distance, right? Because what is distance? Distance is land covered. We can measure it in meters, and what it really is, it's how much land have you covered. It doesn't matter where you are, where you're going, it's just how much land you have physically covered. And you might have covered 0 meters, you might have covered 5 meters, 10 meters. Also, you could have speed. And you can measure speed in meters per second or kilometers per hour. It's up to you. And speed is how fast you cover the land. So if you're at rest at 0 meters per second, you can cover the land at 10 kilometers per second, 20 kilometers per second, right? It's up to you. Now, all those quantities, we were able to measure them using only a one-dimensional number line, right? It's just one dimension. If you look at it, it's just one line. You don't need any more dimensions. However, we also have quantities for which we need to use more than one number line to describe it. And in order to do that, we need tools to capture all the information that happens on one line and on another number line. For example, let's consider this 2D plane, and on this 2D plane we measure position. We measure position of this human here, and also we have this little model airplane, and we denote the position of the human P1, the airplane P2. Now notice that this is not a function here. A function is a mathematical relationship between two variables. However, here we just measure position of objects. So this is the real world. You have a house, you have someone here, you have a model airplane. We are using a rectangular grid system to measure the position of objects, all right? So this is not a function here. So in order to measure the position of this guy here, or girl, we would say something like this. P1. Okay, we know that this person is 10 meters, and we measure it in meters. We know that it's 10 meters in X direction. So that's one number line. However, it's a 2D plane. So how do you know where exactly that person is? That person might be here, or here, or here underground. You don't know. So you also have to specify the second dimension. And For that, we use vectors. The mathematicians have invented vectors, and vectors are tools that enable us to capture information that require more than one number line, right? So we have more than one number line, and we use vectors to capture information. So the way we would describe this position here, position 1, we denote vectors with this upper small arrow on top of the letter. And then we say that, okay, P1 is X and Y. So the X dimension goes first, and then the Y dimension comes later. And then we just say 10 and 0 meters. And now we have fully described the position of the person. And the same thing with the airplane. You can just say P2 X Y, and it would be minus 20 and 15. Minus 20 in the X dimension and 15 in the Y dimension, meters. So this is called a two-dimensional vector. So these quantities here, right, for which you only need one number line, you call them scalar. And here, this is a vector. And essentially, if you think about it, then scalar is just a one-dimensional vector. And of course, in real life, you also need to measure the position in 3 dimensions. So again, this is not a function here, it's just you're using a cubic grid system. Like you see, there's a little cube here. So you have divided your world into little cubes, and now you're measuring the position using the cubic grid system. So let's say that there's something here, right? Maybe another airplane, for example, in this position. And as you can see, you need 3 number lines to determine the position. Let's call it P3 to determine the position 3. You need an X number line, you need Y number line, and you need a Z number line. So for the X it would be 20 meters, for the Y it would be 30 meters, and for the Z it would be 40 meters. And the way you would write it very simply, P3 arrow X, Y, Z, and it would be then 20, 30, and 40, right? 20, 30, and 40. So this is a 3-dimensional vector that represents the position of an object in a 3-dimensional space. But we also have situations for which you need a lot more number lines, not only 3 number lines. So you can have vectors that have a lot more dimensions than 3 dimensions. And of course you can't really represent it graphically, especially if you try to represent them geometrically. However, you can have quantities for which you have many number lines, and in principle you can have as many dimensions as you want or need up until infinity. So that really depends on your context, and I'm gonna give you an example of that. So here you can see a small water storage building, and inside this building you have 5 tanks, and you can also see some pipes here through which water can flow in and flow out. And here you can see how much volume of water you have in each tank. So in the first tank you have 5 cubic meters, in the second tank you have 3 cubic meters, in the third 8 cubic meters, etc. If your objective is to know the total volume of water in the entire building, then of course you only need a one-dimensional vector or a scalar. So what you would do, you would simply add them up, right? Volume total, and then you would just add them all up. 5 plus 3 plus 8 plus 4 and plus 7 would give you 27 cubic meters. And for that you only need a one number line, right? M cubed, and then you have 0 here, and then let's say you have 27 cubic meters here. However, what if your objective is to know how much volume of water you have per tank? Now for that, you need 5 number lines, right? You need 1, 2, 3, 4, and 5. So you have tank 1, tank 2, tank 3, tank 4, and tank 5. And in order to represent the volume of water per tank, again, you would use a vector for that. So you would write something like this. The total volume of water would be V1, V2, V3, V4, and V5, and you represent them like this: 5, 3, 8, 4, and 7. And now you have a 5-dimensional vector that stores the information about the volume of water per tank. You see, you can have as many dimensions as your context demands from you. And you can do that with vectors because vectors were invented exactly for that, to store information of quantities that require more than one number line. You can also graph vectors up until 3 dimensions. So I have taken the two situations from the previous video, where we measured the position on a 2-dimensional plane and in a 3-dimensional space. So we had a person here and a model airplane. The way you graph vectors, simply take the two number lines that describe someone's position and you put them perpendicular to each other, like we have done here. Now I want to specify that this is not the same like this. This is the real world, and we have chopped the real world into small little squares. So we're using this square grid in order to specify the exact position of objects in this world. But this is the real world. You have people here, airplanes, houses, cars, whatever. Here, you don't have those things. This is not a world. Here you simply take the two number lines. In this case, we have number line X and number line Y. No humans, no airplanes. You simply take those two number lines and you put them perpendicular to each other. And then you can grab vectors on this XY plane. But this XY plane, it's not the world. It's not like this. It's just two number lines that have numbers on it. They are placed perpendicular to each other. And the way you graph vectors is very simple. You simply look at the coordinates of position 1, for example, and then you graph it like this. So the beginning of the arrow, which is here, that's the beginning of the vector. And the end of the vector, the tip of the arrow, that's the end of the vector, right? So the way you think about it is that, okay, I go from 0, 0 to x equals 10 and y equals 0. And for the position 2, I go from 0, 0 to x equals minus 20 and y equals 15. And then I graph it like this. And in the end, I have this arrow that points you in a direction. You can think of it like that. Vectors are also thought of as something that describe the direction of a physical quantity. Now, in 3 dimensions, it's just the same. You have 3 number lines and then you put them perpendicular to each other. And again, this is not the same like this. This is the real world. Here you have a house. Here you just have three perpendicular number lines to each other. They don't represent the world. They're just three number lines put perpendicular to each other so that you could somehow graph a vector geometrically. And again, the position 3 had 20, 30, and 40 in the x, y, and z direction. So you go x20, y30, and then you go up by 40. So you're here, your position 3 is here, and then you start from 0, 0, and you go to position 3. And you start from 0, 0, and then in the end you have this arrow. Now, you can also project vectors. What does it mean when I say I'm gonna project a vector on an xy plane? Projecting a vector onto something means losing a dimension. So if I project this vector here on an xy plane, then what I will have this vector here. So I start from here. I have information about 3 dimensions. I have x, and then I have y, and then I have z. So I have information in 3 dimensions. Projecting a vector means that I lose information about 1 dimension and I only see this vector in 2 dimensions. So for example, let's say that I take this coordinate system and I rotate it in such a way that I don't see the z-axis, right? So I just rotate it. And by the way, there is a convention because our sheets of paper are 2-dimensional, but sometimes we want to draw 3-dimensional pictures. So there is a convention that, okay, if I have this kind of sign, then that means that the axis is pointing out of the paper, like this, out of the paper. And if I have something like this, then the axis is pointing into the paper, into the plane. And you can think of it as an arrow. So let's say if I have some kind of arrow here, then I have the tip, and then here in the end I have these little wings to increase the stability of an arrow. That if this arrow points up like this, like out of the plane, then you would see a circle and then a small dot inside the circle, which would be the tip. But if the arrow points down, it points into the plane, then you would see the wings here. You would see like a cross, right? So this would be like positive z direction, and then this would be a negative z direction. So that would be the convention. We're gonna graph the same coordinate system like this. So we have z here, and then we have x here, and then we have y here. Now if I do that and I don't see the z-axis, then I don't have the information about the height of this vector, right? The only thing I'm gonna see is this vector, right? It's projected onto xy plane. And then of course, if I take this line here that goes like this, it's perpendicular to this vector. But you can imagine it, right? If you turn this system like this so that you don't see the z-axis, then you will have something like this. So you have projected the xyz vector onto xy plane. And then once you have projected the vector onto xy plane, then you know that, okay, x was 20, and then y was 30, right? And then z you don't know anymore because you have lost the information about it. And then you can also project the vector, for instance, onto y-axis, right? And again, if you do that, then this would be perpendicular to this line here. And again, think of it like you rotate this 2-dimensional plane now in such a way that the x will point out of the plane. And of course, if you do that, you might think that, okay, then the z-axis will appear, but we assume that it doesn't appear. We have lost information about z, and that's permanent. And now we're going to rotate this axis again, and we have something like this. This is the x-axis pointing up, and then you have y-axis here, and then you have 30, and there you go. You have a vector that is y30. So you see, first of all, you had a three-dimensional information, then I lost that information. I had something like this, right? It's like projected onto xy plane, and then I also decided to project it onto y line. So what I did, I rotated the axis again, so now I don't see the x-axis and I only see the y-axis, so I only have information in one dimension now. And that's what projecting vectors is. It's like losing information about some kind of dimension. And in fact, the same logic applies in functions. For example, if you have some kind of function, let's say you have z here, and then you have x here, right? And then you have some kind of parabola. However, what if I create one more dimension? Well, you can think of it as this line or this curve will become into a surface, and then you would have the y-axis here, and then if I were to project the surface onto zx plane, then I would look at y like this. I would have y, and then I would have here z, and then I would have here x. I wouldn't see the parabola in 3 dimensions. I would see it only in 2 dimensions, and I would only see a curve, 2-dimensional curve. By the way, I really want to emphasize that vectors are not functions, because functions, they represent some kind of relationship. So in this case, z is a parabola because of x. So x is an independent variable, right? You have an input, x, then you have some kind of function, and then you get z. So function is a mathematical relationship. Vectors, well, they're just facts. For example, the position 2 that modeled the position of a model airplane, the x is minus 20 and y is 15. So this is a very important distinction. Welcome back. So I would like to talk a little bit more about how to graph vectors, and I have put this previous example about the water storage building, and then we had 5 tanks, and then we ended up with a 5-dimensional vector. Now, how would you graph a 5-dimensional vector? Well, let's say that if you only had 3 tanks, then you could do it, because then you could do something like this. You could have one axis here, another axis here, and then another axis here, and then you could have V1, which is tank 1, which is cube meters, V2, and then V3. And then V1 was 3, V2 was 5, and then V3 was 8, right? And then you would graph it like this, just like in the previous example with the 3-dimensional position, with a 3-dimensional space where you determined the position 3. And then you would just graph it like this. You would have a point here, and then you could just graph it. Here you have an arrow, and then you would graph it. So you would first go 3 units here, then 5 units here, and then 8 units up. And then from the origin, you can graph the vector. Okay, but that's as far as you can go. Of course, you can't graph a 5-dimensional vector, at least geometrically. You can find other out-of-the-box solutions. However, geometrically, since in geometry we only have 3 dimensions, you cannot go further than 3 dimensions. So it's better to leave it in the mathematical form and work with that, and no need to graph it. A little bit of more terminology. First of all, when I take my number lines and then I make a vector out of them, then the process is called vectorizing. So I vectorize these number lines and then I get a vector. I can choose to vectorize into 2 vectors. I can either have a column vector or I can have a row vector. So depending on my situation in my world of science or engineering, then based on convenience, I will either vectorize them into a column vector or into a row vector. And then, if I want to go from a column vector to a row vector, or from a row vector to a column vector, then I take a transpose. If I take a transpose of a column vector, I will get a row vector, and vice versa. So taking a transpose is another operation. What it does, that if you have a column vector, then it will make this column into a row. So you see 5, 3, 8, 4, 7, 5, 3, 8, 4, 7. And vice versa, 5, 3, 8, 4, 7. If I take a transpose of it, I will get 5, 3, 8, 4, 7. So rows become columns and columns become rows. I want to have a small disclaimer here. So sometimes people put different nature of vectors into one vector, but that can be confusing. I mean, you can do that, but you have to be careful. For example, sometimes people write the position vector. Here they will also write the volume of the tank vector, the total volume of the tank. And then you would have a vector which would be 30, 40, and 50. That's the position part. And then you would have 5, 3, 8, 4, and 7. So that could be confusing because you have 2 different types of vectors inside one big vector. So if you do that, at least I would recommend you to have a horizontal line here just to differentiate between them. And then I would really advise you not to try to graph vectors that have elements that are from different nature. For example, if I have a vector that describes the volume of the tank, and then also some kind of position in one dimension, then if I try to graph it, then I could have something like this. I could have here V1, which would be measured in cube meters, and I could have position that would be measured in meters. And then if you try to graph it, then it just doesn't make sense. Like on one axis you have cube meters, on the other axis you have the length. So it doesn't make sense, it's very confusing, so I advise you not to do it. It just doesn't make sense.